Hi, I'm John, and this is my lab report on Physics 2211, Lab 3, Black Hole. The purpose of this lab is to get a better understanding of the gravitational force through computational analysis and computer simulation of a black hole in spaceship scenarios. We need a couple equations in this lab. First, we need the universal law of gravitation. Next, we need the position update and velocity update formulas for our simulator to calculate the motion of objects. Then we need the momentum derivative expansion to be able to calculate the perpendicular and parallel force components given to us by Newton's second law. We are using the update formulas instead of integration to greatly simplify calculations. The update formula allows the computer to do the work for us. And furthermore, we have to assume that the black hole is not moving because it's multiple orders of magnitude more massive than the star and the spaceship. The system we are studying in the first part of the lab is the star, and the surroundings are the black hole. For the second part of the lab, the system we are studying is the spaceship, and the surrounding are the black hole and the star. The initial conditions for situation 1 is a black hole placed at the origin with a calculated mass of 1.315 times 10 to the 34th kilograms, and a star placed at radius r with initial velocity v and mass of 9 times 10 to the 28th kilograms. For the second experiment, the initial conditions are the same, except there's a spaceship placed on the planet with this initial speed of 3.8 times 10 to the 7th, or an initial velocity of this. Let's now review the details of the coding for the first experiment. First, we have the randomization based on email address. Then we had to specify the star's mass and delta t to be 1 day. Following along, we have to calculate the total momentum. Use that to find total force. Then we know that total force is equal to our gravitational force because that is the only interaction between systems and surrounding in our situation. We use the derivative expansion of the momentum formula to calculate dp dt parallel, and we know that because there's no other forces, dp dt perp is going to be f net minus dp dt parallel, or just dp dt minus dp dt parallel. Then we append the current force at each position so that we can find the total mass of the black hole later. This is just for drawing our force arrows. And finally, we have the black hole's mass being equal to the sum of the list that we made earlier divided by the length. This is essentially the average force of our calculation, which is going to give us the average mass that we calculated. Here's the first program running. For our second program, we have the inputs as constants from the previous simulation. We have our initial speed, which we specified. For this example, we have the initial speed for our slingshot trajectory. Then we have calculating the force on the planet as well as on the ship. We ignore the black hole once again because it's many orders of magnitude greater, and so therefore we're saying it doesn't move. And then we update the position and the velocity of the ship. And here we have if it crashes into either the planet or the black hole, the simulation ends with an error message. We also have, for tracking the speed of the ship, I print it every 100 seconds. And here's the program running. Our assumptions made to simplify the calculations and deviations from analytical solutions may present some error in this lab. Now let's answer the what if and what does it mean questions. For part 1 first, the perpendicular component of the net force is the force of gravity acting on the planet, and the parallel component of the net force is 0. However, the rate of change of momentum in the perpendicular is really the change in direction of the momentum, whereas the rate of change of momentum in the parallel direction is change in the speed of the star, which should be 0. It is not 0 because of the update formulas and assumptions we used, as well as the direction of p hat being set equal to p final. Question 2. Instead of waiting to take a quick look, we want to enter an orbit. Here is an example of velocity which would produce an orbit. Here's an example of velocity, initial velocity, that gives us an acceptable orbit. This orbit takes around 3 hours to complete. if we just wait for the simulation to be done. Just a second here. You can see the initial speed and velocity of the ship right here.